Welcome, my dear students. We are going to study evidences for the formation of coordination compounds. Formation of complexes or coordination compounds can be confirmed by a number of experimental evidences which indicates the complex ion formation. Various experiments are the methods used to detect the formation of complexes. First, that is the color change. Formation of complexes ions from a simple ion is usually followed by a color change. When a pink solution of cobalt plus 2 ion is treated with a high concentration of Cl minus ion, it turns blue due to the formation of complex ion, the tetrachloride cobalt 2. Cobalt plus 2 pink color plus 4 Cl minus gives the COCl 4 in bracket 2 minus blue color complex. Similarly, when yellow Ap plus 3 solution is treated with SCl thiocyanide, a red colored solution is formed due to the formation of complex iron thiocyanide 2 plus there is a state, oxidation state, Ap plus 3 yellow color plus SCl thiocyanide, it gives ApSCl in bracket plus 2. The Ap plus 3 it is in a yellow color and the Ap it is goes to the plus 2, the red color. Consider an aqueous solution of copper plus 2 ion. It is a light blue in color. When ammonia is added to this solution, it turns deep blue in color due to the formation of a soluble complex ion. The CuNH4 S2O twice in bracket 2 plus the CuS2O6 in bracket 2 plus hexa echo copper 2 light blue color plus 4NH3, it gives CuNH3 4 S2O twice in bracket plus 2, means there is a bis aqua tetraamine copper 2, it is a deep blue color. Identification of a complex ion can be carried out by its absorption spectrum characteristic, that is the position of maxima minima in the absorption spectrum and their intensities. Another, that is the change in solubility. Some complexes are soluble in aqueous solution. When to an aqueous solution of Ag plus ion, Kcn solution is added in a limited proportion. Addition of Cl cyanide ion to aqueous solution of Ag plus ion precipitates as AgCl. Ag plus plus Cl minus, it gives AgCl as a precipitate of AgCl. In addition of KCl is continued, then excess cyanide ions leads to the formation of a complex AgCl twice in bracket minus 1, means dicyanosilver, due to which the solubility of AgCN increases. The AgCN plus Cn minus, it gives AgCN twice in bracket raised to minus 1. Thus Ag plus Cn minus, it AgCN it gives sparingly soluble. Then excess of KCN gives a K in bracket AgCN twice, then soluble complex, then it gives K plus AgCN twice in bracket raised to minus 1. The complex ion AgCN2 twice is a cyanide complex of silver, that is a bis or dicyano silver is a complex ion soluble. Other example, complex are soluble in aqueous solution. Ag plus Cl minus is equal to AgCl sparingly soluble. AgCl plus excess ammonia, it gives the Ag NH3 twice in bracket Cl. Diamine silver chloride complex soluble then it is equivalent that equilibrium with the Ag NH3 twice in bracket plus means diamine silver 1 that is a complex ion is soluble plus Cl minus. Some complexes are less stable in an aqueous solution and hence are precipitate on the formation. For example, nickel DMG twice dimethyl glycine meto nickel is insoluble in an aqueous solution and hence it is precipitate when ammonical nickel plus 2 solution is treated with dimethyl glycine. Another that is a conductivity measurement. The complex formation results in a change in the value of electrical conductance of the solution. Molar conductivity of the dilute solutions, that is salt solution, is due to the number of ions present in a solution. When a complex ion is formed, the number of ions in a solution will change, resulting in the sudden change in the molar conductivity. Therefore, a sudden appreciable change in molar conductivity of the solution indicates the complex formation. Consider a 1 molar aqueous solution of copper acetate. If the 2 molar glycine solution is added to it, the conductivity of the solution decreases due to the formation of non-ionic chelated complex. Another that is the change in pH values, that is the pH measurement. In a reaction, if a formation of a complex involves the change in H plus ion or OH minus ions concentration, then change in the pH of the solution will indicate the formation of a complex. For example, during the formation of metal complex with the EDTA, oxalate C2O4 twice minus etc., the H plus ion concentration increases, hence a decrease in pH indicates the complex formation. Generally, ligands are either weak acids or weak bases. The formation of a complex is accompanied by the displacement of one or more acidic protons of the ligands by the metal ion, which results in the increase in H plus ion concentration, hence in causing a drop in the pH value. Consider addition of a solution of sodium salicylate to the aqueous addition of Ap plus 2. A phenolic proton is liberated, resulting in the increase in concentration of H plus and thus a decrease in pH of a solution. The stoichiometry of the complex formation can be deduced using the pH metry. Thus, the change in the pH value can be used as an indicator of the extent of complex formation. Another that is the ion exchange studies. Simple metal ions, that is the cations and cationic complexes, will be adsorbed by cation exchange region. Anion complexes will be adsorbed by anion exchange region. There is cation exchange region, anion exchange region. While non-ionic complexes are not adsorbed by the cation or anion exchange region. If solution containing Zn plus 2 or the Ap plus 3 ions is passed through anion exchange region, Zn plus 2 ions are not adsorbed, not retained on that region by the region. If the Zn plus 2 solution is treated with the excess of HCl, it forms an anionic complex, means a zinc chloride complex, ZnCl4 bracket 2 minus, means a tetrachloro zinc. 2. Zinc plus 2 plus HCl in excess, it gives a zinc chloride, the anion complex ion, ZnCl4 raised to 2 minus, so anionic complex ion. Ap plus 3 plus HCl in excess, it gives ApCl4 in bracket raised to minus. It is also anionic complex ion. This complex anion, that is a zinc chloride complex, is adsorbed by anion exchange region, or it is retained in by anion exchange region but not by cation exchanger. The potentiometric measurement. Another that is the potentiometric measurement. In reaction, as a complex formation takes place, The concentration of metal ion in the solution decreases, hence the change in the electric potential of the system. The concentration of ligands can be followed to the detect complex formation. Means metal ion versus the concentration of the ligands. When metal ion combines with the ligands to form a complex, its ionic activity decreases and its oxidation potential increases. For example, cobalt plus 2, it converted to cobalt plus 3. The electron is released. The electrode potential is minus 1.84 volts. When the complex hexaamine cobalt 2, it gives the complex hexaamine cobalt 3. The electrode potential is a minus 0.10 volt. Another tris ethylene diamine cobalt 2 is converted into tris ethylene diamine cobalt 3. Means cobalt 2 is converted to cobalt 3. Cobalt 2 tris ethylene diamine cobalt 3 tris ethylene diamine formation. That time there is a electron potential E raised to 0 is equal to minus 0.26 volts. Then another example, that is Fe plus 2 is converted to Fe plus 3 plus electron. Electron potential E raised to 0 is equal to minus 0.771 volts. Means the cyanide complex in Fe plus 2 and the cyanide complex in Fe plus 3. Means Fe plus 2 converted into Fe plus 3 hexacyano complex, that is the iron 2 is converted to hexacyano Fe plus 3. The potential is minus 0.36 volt. Then the phenyl iron triphenyl converted into iron triphenyl iron Fe plus 2 converted into Fe plus 3 complex. Means there is a potential minus 1.14 volts. Oxidation potential of metal ions in a solution and in the complex ion are different. The difference can be taken as evidence for the complex formation. The another, that is the change in chemical properties. When a metal ion combines with the ligands to form a complex, its usual chemical properties are lost in the solution. Consider a solution of FeCN twice. It will give a test for Fe plus 2 as well as Cl minus. When this solution, KCN solution, is added, it forms the complex potassium ferrocyanide K4FeCN6. This solution will not give a precipitate of iron hydroxide FeOH twice. When treated with NaOH, that is test for the Fe plus 2, but will give a brown precipitate of the copper hexacyanoferrate with a copper sulfate solution. That is the test for the complex ion, the copper hexacyanoferrate 4. The K4FeCN6 plus CuSO4, it gives Cu2FeCN6 plus twice K2SO4. Thus, the loss of the normal chemical properties of the metal ions in the solution is an indication of the complex formation. In addition to above methods, other methods which can be used to evidence for the complex formation are migration of ions in electric field with the transference studies, polarographic measurement, measurement of magnetic susceptibility, dipole moment measurement, and a distribution, that is a partition method. Thank you.